Hello, everyone. Um, Today's discussion is we're going to go back to simple harmonic motion and take a look at a couple of features that may be giving you some difficulty. All right, so let's build the spring mass system. It's in one dimension and its solution is straightforward, but let's talk about what it's doing. That's not mass. This is x. Okay. So let's begin this discussion of our string mass system without the spring. So the level surface without friction and let's ask the all-important question, what is x as a function of t in this case? So a block sitting on a frictionless level surface, what we would normally do is say, let me get rid of red. What we would normally say is sum the forces, mass and acceleration, which is the result of our system, which is the block system or the mass system. We draw a free body diagram of this guy. Where the force normal would equal the force of gravity. We'd sum the forces in the y direction. Force normal up minus the force of little g down equals 0. And then the sum of the forces in the x direction. I don't have any forces, therefore I don't have any acceleration. Okay. Let's take the same idea and do it again. Only this time what I want to do is I want to tilt the surface. Some angle theta. And we'll put the block on it. And this will be our axis point. So again, what we would do is sum the forces equals mass times acceleration. System is going to be the block. And again, our question is, which I didn't answer last time, but let's get the question down. What is x of t? Now up here what we found is x as a function of t is just equal to 0 t plus the starting position of the object. So that would give us, on the correct graph, would say the object is sitting here. Alrighty, so where were we? So we would do what we did at the beginning of the semester. We would draw a free body diagram. We'd have the normal force perpendicular to the surface, the weight force coming down, force normal, force of gravity, and remember we're going x and y, and we know from prior experience that we should expect an acceleration down the incline. Thus we will sum the forces in the x direction, and we will sum the forces in the y direction. The forces in the x direction would be there would be a force due to gravity with an x component, and that would equal mass and acceleration. In the y direction, there'd be a force normal minus a force g in the y direction equals mass and the acceleration, which we know here is 0 because the green box isn't tumbling or bouncing down the hill or anything. It's just going. So since we have to decompose Fg, we'll get the Fgy Fgx, the full value of Fg, and our angle theta right there. So this would turn out to be that that Fgx is actually Fg side opposite, so it's going to be sine of theta equals ma, and then Fg is just mass times gravity, sine theta equals mass and accelerations, our masses cancel, and we get the overused result that the acceleration down the incline is equal to g sine theta. So now the question is, what do we do about x? So the acceleration is the derivative of velocity over time. So we'll plug in the acceleration, g sine theta. It'll equal dv dt, multiply both sides by dt, And we wind up with dv equals g sine theta. And all of that is constant in our case. So we're just going to integrate over time. And we're just going to integrate over the velocity during that time interval. And we'll get g sine theta multiplied by the change in time is equal to the change in velocity. If we set the time t equal to 0, then we know that, and let me flip this equation around, that velocity as a function of time is given by the initial velocity plus g sine theta multiplied by the time. dv dt is dx dt, and that's equal to our velocity. So I can write dx as the velocity as a function of time dt. So my change in my x position, because I'm going to take the integral, is going to be the integral of v naught dt plus g sine theta integral of t dt. So delta x is equal to v naught t plus g sine theta 1/2 t squared, if t is equal to t initial is equal to 0. And this is a very familiar equation to you. So we would write this in its final form as x of t is equal to initial x, v naught initial t, plus g sine theta 1/2 t squared. So this is the motion of the block down the incline as a function of time. Now, this is the generic equation, because I can have initial conditions like x naught is 2 meters and v naught is at 0, and that'll give us the specific equation for motion. That x, I always grab that crayon. That x as a function of t for this particular system. So again, this is general, and it's what you've seen before and used a lot of. And then you're very comfortable going back to the specific, where x of t is given by our 2 meters. The 0/2 goes away. We're going to get g over 2 sine of theta, or whatever value of theta is, numerical value it is, and then the time squared. So The thing I want to bring up about simple harmonic motion in this particular quick video is you've been doing descriptions of motion all along. That's one of the things we've been hallmarking, is that you have the ability to do finding what x of t is, because you've been doing it the whole time. So let's do one more example. Let's get our flat surface again, and let's put a mass on this surface a slight distance away from the starting axis, x and y. And in this case, again, our goal is to find x as a function of time. Only now, because we have the proper language, I'm going to put a force on this that is a function of time. So, this is a force problem. So we start with, I'm going to do that at the end of the semester, aren't I? Let me take you and make you a less appealing color so I don't see you. There we go. So we're going to sum our forces. This case only in the x direction, but that's not what I meant to do. So sum our forces in the x direction. And what we'll find is we'll find that the f of t in the x direction is equal to the mass and the acceleration. I think it's worthwhile being specific here. So let's set the force as a function of time to something something harmless. How about 6 newtons over second squared t squared? Okay, so I wind up substituting that in, 6 t squared equals mass times the acceleration, dv dt. Multiply through both sides by dt, and I get mass dv. We'll keep the mass constant, so we slice down here, we slice down here, and we're going to get 6 over 3 t cubed is going to equal mass and the change in the velocity. We're making a note that t is equal to 0. Okay, so now I wind up with, that's 2, let's bring the m over, t cubed is equal to velocity not plus this, and this would be velocity as a function of time. Okay, so we know velocity is dx dt, so we'll have to integrate again. So we're going to go velocity dt plus 2 over m t cubed dt is going to equal dv. So we integrate this, we integrate this, we integrate that, and we get v naught t. Again, I'm setting t equal to t initial equal to 0. Plus 2 over m t to the 4, carry the 4 down, and that's going to equal my change in my, that should be an x by the way, change in my x's location. So here I would write x as a function of time is equal to v naught t plus 1 over 2m t to the 4 plus x naught. So again, we find that there is a description of motion that depends on the specifics of the case. So given that value for a force, we go through the same steps we did at the beginning of the semester, where we solve for time, and then we take apart, we solve in a direction, we take apart the time derivatives until we get ourselves down to the function as a function of x. And then we can use that if you wanted to find the position of the object and such. So in all of these cases, from the very simple and trivial case, wherein we had just a block at rest without any forces on it, which gave us an x of t, which we knew would be just, it's sitting there, so whatever value it has at x naught, over time it's going to keep that value, so we put a 0 in front of time. To the problem we've seen before, where we set the angle, the ramp at an angle, and we wind up getting the the big equation we use all semester. And like we would do all semester, we'd plug it in and go. Then I can give you a complex force, and you can again, just by taking a couple of antiderivatives, wind up down here with another expression as a function of time. So when it comes to simple harmonic motion, all you are doing is saying that I've got the flat surface, my axes, the mass, and then a spring. Still starting at x naught. And our goal would be to find x as a function of time. Okay. We'll solve a couple more cases of simple harmonic motion, just so you can see it. But I want you to notice that when I come up with an expression that looks like x as a function of time equals a sine of omega t plus v, that I'm doing nothing more than what we've done all semester long. I'm just following a process from x of t to find the acceleration and, the velocity along the way if I can. So I hope this helps a little bit.